Welcome to ATMOS 5000, day 27. Our objectives are being pulled from Chapter 2, sections 2.1 and 2.2. We've now completed the Cloud Microphysics module and we're moving on to the Radiation module. So today we're going to talk about the different types of radiation and which kinds are emitted by the Sun. We'll talk a little bit about the orbital parameters and how the Earth actually orbits around the Sun and what impacts that has on the amount of radiation that we receive from the Sun. We'll look at the orbital parameters and how they influence our seasons, and then we'll talk about both the controls and the effects of changing sun angle. So what exactly is radiation? Well, it's the transfer of energy by electromagnetic waves. These waves don't require a medium, they travel at the speed of light, and it only takes about 8.5 minutes for the light to travel from the Sun to Science has decided to classify different types of radiation based upon the wavelength. And the convention is that we have identified 7 different types of radiation, ranging from gamma rays, X-rays, ultraviolet, visible, infrared, microwave, and radio waves. Obviously, the radiation has a continuum of wavelengths, and we just have by convention defined which wavelengths correspond to which of these types of radiation. So the gamma rays have the shortest wavelengths, and the wavelengths get longer and longer until you get to the radio waves. In terms of the amount of energy associated with each of these types of radiation, the gamma rays, which have the shortest wavelength, have the highest amount of energy associated with them, and the radio waves have the lowest amount of energy associated with them. Visible light is composed of 7 individual colors, which we can remember easily with the mnemonic Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. The red has the longest wavelength of 700 nanometers, and the violet has the shortest wavelength of 400 nanometers. And those are important quantities to remember. So the 400 nanometers is equivalent to 0.4 micrometers, and the 700 nanometers is equivalent to 0.7 micrometers. So what is the source of most of the energy that we receive in the Earth's atmosphere? And the short answer is the Sun. Here we have an image of the Sun. It happens to have some sunspots on it right now. However, we are in a time period when we don't have many sunspots, and that's essentially the minimum. The sunspot cycle has an 11-year cycle, and the Sun produces energy through nuclear fusion, and it's basically fusing hydrogen into helium at immense temperatures and pressures inside the core of the Sun. And the surface temperature of the Sun is around 5,800 Kelvin. The radiation that is given off from the Sun peaks in the visible wavelengths. So most of the energy, in fact 44% of all of the energy from the Sun, is radiated as visible light, somewhere between the blue and the red. The peak is green light, but when you add all those colors together, you essentially get white light. We have 7% of the solar radiation is ultraviolet rays, and then we can combine the infrared. We have the near infrared, which is up to about 1.5 micrometers in wavelength. That's 37% of the energy. And then we have what we call the far infrared, which is another 11%. So if you add those two together, you'll get 48% of the solar radiation is emitted as heat energy, which I guess trumps the visible light, which is 44%. And then we have less than 1% of the solar radiation, which is emitted in the long waves of microwaves and radio waves, and a very small percent of the radiation is emitted as gamma rays and X-rays. The orbit of the Earth around the Sun is not circular. It is elliptic, and we are further away from the Sun during certain times of the year and closer to the Sun during other times of the year. When we are furthest from the Sun, we refer to that as aphelion, which occurs in July, And then we're closest to the sun. We refer to that as perihelion, and that occurs in early January. The distance varies between about 147 million kilometers to 152 million kilometers, which is a distance of about 3.4%. So if you want to calculate the Earth-Sun distance on any given day, then these are the formulas that you need to use. So we have R, and the second equation is the Earth-Sun distance is equal to a constant A times 1 minus the eccentricity E over 1 plus the eccentricity times the cosine of this function M. M is essentially kind of defining where we're at in terms of the orbit around the sun. So it equals 2 pi. And then we have the current day of the year. So we start off on January 1 being day number 1 and January 2 being day number 2, et cetera, et cetera. And then we subtract off dp, which is the date of the perihelion, which is the 4th day of the month of the year. And then we have the period of our orbit, which is 365.25 days. So we'll take that M value for a given day, and then we will plug that into the radius equation down below in order to get the actual distance on a given day. As the Earth rotates around the sun, orbits around the sun, the North Pole of the planet is pointing to a fixed point in space. It's pointing towards the Polaris, which is the North Star. And the impact of this is that there are 2 time periods of the year when this, from the perspective of the sun, you can actually see both the kind of the North and the South Pole, and that would be the equinoxes, the vernal equinox in March and the autumnal equinox in September. And then as we move towards the summer solstice, the northern hemisphere is illuminated more than the southern hemisphere because of the tilt of the Earth. And then during the winter solstice, the opposite is the case, and the southern hemisphere is illuminated more than the northern hemisphere. So let's take a look at that. For the northern hemisphere summer solstice, the Earth is tilted, and everything above 66.5 degrees north will receive 24 hours of sunshine. And everything further south than 66.5 degrees south will be in full darkness for the entire time period. During this time period, the days are longer in the northern hemisphere and the days are shorter in the southern hemisphere. For the equinox time period, when half of the planet between the North Pole and the South Pole is evenly illuminated, you essentially have a day length of 12 hours everywhere from high northern latitudes to high southern latitudes. And then when we get to the winter solstice for the northern hemisphere, everything above 66.5 degrees north is completely dark, and everything below 66.5 degrees south is in full illumination for the 24-hour period. The days in the northern hemisphere are shorter, and the days in the southern hemisphere are longer. So the seasons are essentially opposite. We have the northern hemisphere winter solstice is the southern hemisphere summer solstice. So we can define the solar declination angle as the tilt of the Earth's rotation to the ecliptic plane, which is 23.44 degrees, times the cosine of this function, which is basically the 2 pi times the current Julian day of the year, d minus dr, which is the day of the summer solstice, which is typically around June 21st, but it can vary by a day or two. If the summer solstice is June 21st, then that's day 120 or 172. And then we divide that by dy, which is the number of days in the year, which is 365. and that will give you the solar declination angle for a given day of the year. We can also define the elevation, azimuth, and zenith angles for the sun. Phi here is the elevation angle, and so the sine of phi is equal to the sine of the latitude times the sine of the solar declination angle minus the cosine of the latitude times the cosine of the declination angle times the cosine of a function, which basically figures out what time of day you are at. We have a c, which is a constant, times our time at UTC, so that's the time at Greenwich, England, divided by 24 hours plus your longitude. So it takes into account where you're at on the planet. We can also get the azimuth angle of the sun. That's the cosine of alpha, where alpha is the azimuth angle. And that's going to be equal to the sine of the declination minus the sine of the latitude times the cosine of the zenith angle divided by the cosine of the latitude times the sine of the zenith angle. And the zenith angle is defined essentially as 2 pi over 4 minus the elevation angle. So let's do a critical thinking exercise and trying to determine if the changes in the Earth-Sun distance actually were responsible for causing the seasons. Well, here's what we know. We know that the Earth is closest to the Sun in January and farthest away in July. So the Southern Hemisphere summer is in January, and the Earth is closest to the Sun in January, so that would be consistent. And the Southern Hemisphere winter is in July when we're furthest away, so that's consistent. However, the Northern Hemisphere winter is in January. So our winter season, we're actually closest to the Sun, and the Northern Hemisphere summer is in July, so the Northern Hemisphere summer, we're actually furthest away from the Sun. So the timing of this is correct for the Southern Hemisphere, but not for the Northern Hemisphere. So the answer really has to be no, that the changing Earth-Sun distance is not responsible for the seasons. So what causes the seasons? Well, primarily it's changes in the sun angle and the changes in the length of the day and the night. And both of these are caused by the 23.5 degree tilt of the Earth. So essentially, if we had a 0 degree declination, as shown in the bottom left, as we orbit the sun, we wouldn't have seasons because every place on the planet would be illuminated by 12 hours of sunlight and 12 hours of darkness during the day, and the sun angle would only be a function of latitude. But because we have a 23.5 degree tilt, that apparent solar angle varies throughout the year. And you can see that if at 0 degrees we have no seasons, at 23.5 degrees we have stronger seasons. The strongest seasons would actually occur on a planet that has a 90 degree tilt. And that is, we do have that situation for one of the planets in our solar system. So let's take a look at the effects of changing the solar angle. So here we have an experiment. I would normally do this in class, but I'm going to do this in the PowerPoint. We have a flashlight that's pointing directly down on a surface, and that is a direct overhead sun. And then we're going to change the angle of the flashlight, and we're going to see what that does to the sunlight as the angle changes. So here we have a solar, essentially a zenith angle of 0. So we have a direct overhead flashlight, and it illuminates a circle that's quite bright. I made it red just because red is easier to see than yellow would be in this demonstration. So we changed the solar zenith angle, or the flashlight zenith angle here, to 15 degrees. And what happens? Well, the area of illumination actually increases. but the overall intensity of the light decreases. And you can see that as we move to higher and higher angles. 30 degrees. Once again, the area of illumination has increased and the intensity has decreased. Same thing at 50 degrees. And now we have 70 degrees. We still have the same amount of energy striking the surface. That's remaining constant. And we quantify the amount of energy striking the surface in terms of watts, W, which is a joule per second. But then we're looking at the flux of energy, which is the watts per meter squared. And that energy flux to the surface is being reduced by changing the zenith angle. And it's quite dramatic. And by the time you get to 90 degrees, the illumination essentially goes to zero. So we can have a mathematical relationship for that, where if S is the amount of sunlight that you receive as a function of zenith angle, that is going to be equal to the amount of solar radiation that you receive at the top of the atmosphere times the cosine of the zenith angle. So when the zenith angle is 0, the cosine of 0 is 1, and you get the maximum amount of radiation. And of course, when the cosine of the zenith angle, for a zenith angle of 90, that would go to 0, and you would essentially get no flux at the surface. And that sun angle, can be affected by latitude, by time of day, by season, and by the slope of the ground. Let's look at these individually. So the impact of latitude on the sun angle. So this actually lists the sun angle for each of these latitudes. So if you look at the equator, it says that the sun angle is 90 degrees. So that's essentially a zenith angle of 0 degrees. And as we move northward, the sun angle decreases from 90 degrees to 66.5 to 45 to 23.5 and eventually to 0. So the zenith angle is essentially going from 0 to 90 degrees as you move from the equator to the pole. So what impact does that changing sun angle have on the amount of radiation, the flux of radiation that is received at the Earth's surface? So at the top of the Earth's atmosphere, the solar constant, or the amount of radiation that we receive from the sun, is essentially 1,361 watts per meter squared. So if we look at the equator, where the solar zenith angle was 0 degrees, then the cosine of 0 is 1, and you receive essentially the theoretical maximum amount of radiation of 1,361 watts per meter squared. In reality, you will not receive that much at the Earth's surface because the atmosphere both scatters and absorbs some of that radiation, but we'll just ignore the presence of the atmosphere right now. So as you move to the Tropic of Cancer, so that's 23.5 degrees north, then you'd use the cosine of 23.5 degrees, multiply that by our solar constant, and the amount of energy that is received, the maximum theoretical would be 1,248 watts per meter squared. By the time you move to 45 degrees north, where you're in our neck of the woods here in Utah, then you use the cosine of 45 times the solar constant, you get 962.4 watts per meter squared. And by the time you get to the Arctic Circle, you're at 543.7 watts per meter squared, which is a significant reduction in the strength of the radiation that is illuminating the surface. And that's due to the curvature of the Earth. So how does time of day have an impact on sun angle? Well, obviously, when the sun is directly overhead, or at local noon anyway, the sun is as high in the sky as it's going to be. And as you move towards either sunrise or sunset, the sun is getting lower and lower in the sky. So why is a low sun angle weaker compared to a high sun angle in terms of the illumination? Well, let's look at why that is the case. So we're going to talk about scattering and absorption in the atmosphere. So early on in the day, say near sunrise, the sunlight is passing through a longer path length of atmosphere to get to a receptor at the Earth's surface. And so that gives it more opportunity for scattering and more opportunity for absorption, which means that ultimately less radiation actually makes it to the ground at that point. So if we look at the impact of season on sun angle, so we know that the tilt of the Earth has an impact on the apparent solar elevation angle, but what it really does is it alters the path of the sun through the sky. So in the northern hemisphere for a June 21st solstice, the sun is rising in the northeast and setting in the northwest, and it's making its highest approach on the longest day of the year. Will have the highest sun angle. At the equinox, it will be the sun will be rising directly in the east and setting directly in the west. And this maximum sun angle will be defined essentially by the latitude. So if you happen to be at the equator on this day, the sun will stay in that east-west plane and will rise directly in the east and will set directly in the west. And of course, the winter solstice for the northern hemisphere, the sun will rise in the southeast and set in the southwest and will have a relatively low maximum sun angle. So ground slope can also have an impact on the apparent sun angle. So here we have a sun angle that's 45 degrees above the horizon, and the ground slope is essentially level. But if we alter the ground slope, it will change the apparent sun angle for that surface. So here we have a 20-degree slope, and what that has done is it's actually increased the apparent sun angle for that particular slope. And what that has done is it will increase the flux of radiation, or excuse me, the amount of radiation received on a watts per meter squared basis for that southern exposure, if we're in the northern hemisphere. So you can see this quite commonly in the northern hemisphere. If you have snow in the mountains, the south-facing slopes will typically melt out faster than the north-facing slopes, in part because the strength of the solar radiation on a per meter squared basis is much higher on those southern-facing slopes than it would be on the northern-facing slopes. So that greater sun angle makes the sunlight more intense.